Hello and welcome to our next lecture in CHY 113. Last time we started our discussion of the energy involved in chemical processes. We began with some of the very basic principles of energy, then went on to discuss specific heat capacity and the ability of a substance to gain or to lose energy, and gave the symbol of C to that for specific heat, and talked about how we use that to calculate heat Q using our equation Q equals mc delta T, which will be an equation that we use a lot throughout all of this energy unit. From there, we're going to pick up our discussion today and talk about the energy involved in changing states and changing states of matter. We'll move from there to discuss the first law of thermodynamics a little bit, that energy cannot be created or destroyed. And that becomes important for us because the energy of various chemical processes often can't be measured directly. But what we can do is measure the energy given off by a reaction, for instance, by measuring how much energy is transferred to water, which we can measure directly. And so we'll talk about how we do that. And from there, we'll discuss how we visualize and how we represent the energy given off in chemical reactions in a thermochemical equation. And lastly, today we'll leave off with discussing calorimetry, which is one of the methods that we can use to experimentally determine the energy involved in various processes. And so let's go ahead and get started with the energy involved in changes of state. And so last time, once again, we discussed calculating energy by using Q equals mc delta T. And we can use that equation as long as there is a temperature change, because remember, specific heat capacity relates to the amount of energy required to raise or to lower the temperature of a certain substance. When things are in the process of a phase change, however, what we're going to see is that there is not actually a temperature change. When something is melting, for instance, it's in that process of going from a solid to a liquid, the temperature itself does not change. All of the energy is put into disrupting the forces that hold the atoms together. And so we don't actually have a temperature change. And so we're going to look at how we can calculate the amount of energy required to do something like that. And so, for instance, if we sort of just take a look at this example here, if we transfer 500 kilojoules of energy into 2 kilograms of ice, which is at 0 degrees C, all of that ice will melt and become water at 0 degrees C. Or sorry, not all of it. All of the energy will go into melting the ice, and we'll be left with a little bit of the ice left over. We'll be left with about half a kilogram left. Both the solid and the liquid are at the same temperature. Like I said, that temperature isn't actually changing. All of the energy is simply going into melting the solid. However, if we put that same 500 kilojoules of energy into 2 kilograms of iron, which is at 0 degrees C, the temperature is going to increase. And we're not going to change the state. And that has to do with the various properties of water versus iron. And so let's take a look at what we call a heating curve and look at what happens as we do add energy into a substance. And so we can see here, and we'll run through this calculation in just a little bit, of if we have 500 grams of water at solid ice at negative 50 degrees C, and heat that all up till it's steam at 200 degrees C. We'll look at how to calculate that in just a minute. But first, let's take a look at just what a graph of the temperature change would look like at this point. And so at this stage down here, at our very first stage in our graph, we're sitting here at solid ice. So we're at 100% solid right here. So this is solid ice at negative 50 degrees C. Now we begin to add heat to this. We begin to add energy until we get to the melting point of water at 0 degrees C. At this point, like I had mentioned, all of the energy is now going to go into disrupting the forces that are holding the water molecules together. We are not going to raise temperature at this point. Along this portion of our heating curve, now we're melting. We're sitting here at 100% solid at 0 degrees C until we've now added enough energy at this point to be 100% liquid at 0 degrees C. But our temperature has not changed. All we are doing along this portion of the curve is actually melting the ice. Once we get to the stage where we have 100% liquid, now we're going to start warming it up again. Now we're still putting heat into this. We've been adding heat this whole time, but now the heat, now this energy that we are putting into the system can once again go into warming up the water. And it's going to do so, and it's going to continue to warm up until we get to the boiling point of water, until we get to 100 degrees C. Now, once again, we're hitting a phase change. 100% of the heat that we put into this system at this point is going into boiling the water. It's going into converting us from liquid water at this point to gaseous water all the way over here. We're still at 100 degrees C. Our temperature has not changed whatsoever. We're simply going from 100% liquid to now 100% gas, still at 100 degrees Celsius. All of the energy at this point is going into liberating the water molecules from their liquid state and sending them into the gas phase. Remember, we visualized that like this. Here's our liquid water sort of just all rolling over each other. Then we put more and more energy in until now the water molecules are just dancing all around and banging into each other. And so that energy that we're putting into it from this point to this point is going into that process, getting us from looking like this at a molecular level to now jumping all around and zooming all around. Now we're at this point with all the water in there is in the gas phase. Now we can start heating it up again. Now we start getting hotter and hotter steam. And so incidentally, this is why if you think about boiling water, so think about water at 100 degrees C versus steam at 100 degrees C. The same exact temperature. And this is where we can start to really see the difference between temperature versus heat. So the same exact temperature here versus here. Which one would you rather stick your hand in? I mean, ideally neither, but if for some weird reason you had to choose, I would much rather stick my hand into boiling water at 100 degrees C rather than have to stick it in a bunch of steam at 100 degrees C. Same exact temperature, yet the steam has so much more heat. There is so much more energy in the system when it's steam. And so very big difference there between temperature and heat. Same temperature, but the steam's going to do a lot more damage to you. And so it's just something to keep in mind when you're thinking about that difference between temperature and heat. And so we've seen ways, we've talked about ways to calculate the amount of heat required for this portion, and this portion of the curve. That's just our Q equals MC delta T. Take our mass of the water, multiply it by the specific heat, multiply it by our temperature change. That gets us to our Q value. That gets us to our heat. What we need, though, is also a way to calculate the heat involved in these portions of the curve, the heat involved in melting our substance and the heat involved in boiling our substance. And so here we're going to introduce a couple other properties of water, or properties of substances in general. So we'll look at this calculation. Sorry, let me go back a little bit. And so if we want to calculate this, if we want to calculate the amount of heat required to actually perform this, to go from negative 50 degrees C to 200 degrees C with 500 grams of water, we have the 5 basic steps that we were just looking at on our chart. First, we've got to warm the ice up to get to 0 degrees Celsius. Then we have to melt the ice. And this is just the same as our chart. We're just looking at it in steps now. Now that we've melted the ice, we now have to heat the liquid water until it gets to the boiling point, until it gets to 100 degrees C. And then we have to boil it. We have to evaporate all of the water, get it into the steam, into the gas phase. And finally, we have to heat the steam up until it gets to 200 degrees Celsius. So we have to go through all 5 of those steps. And in order to actually calculate the total amount of heat, we need to calculate each of these 5 different steps, calculate the heat involved at each of those steps. So we calculate the Q value for each step, and then we just add them up to get our total amount of heat. We would just add up all those different Q values. Again, like I said, we've talked about how to calculate the amount of heat for the portions of that curve where the temperature is rising. That's just our Q equals MC delta T. What we need, though, is a way to calculate the amount of heat required to melt and then the heat required to vaporize. And for those, we're going to use the heat of fusion, which is the amount of energy required to transform a substance from a solid to a liquid. So the amount of heat required to melt something. We're also going to talk about the heat of vaporization, which is the amount of energy required to vaporize something, the amount of energy required to take a substance from the liquid phase into the gas phase. And we can see some of those values here for some various substances. We're looking, for instance, at water. The heat of fusion is 333 joules per gram. The heat of vaporization is 2,260 joules per gram. Now you'll note the difference in units. This is a key distinction to make. When we talked about specific heat, our units were joules per gram degree C. Because specific heat, we're looking at the amount of energy required to change temperature. With these phase changes, remember, we're not changing temperature. And so degree C does not show up in our units. Temperature does not show up in this part of the calculation. The only thing that will change the amount of energy required is how much of the substance we have. How many grams do we have? And just take note here that we symbolize heat of fusion by delta H fusion, FUS, and heat of vaporization with a delta H VAP. And so you would see, for instance, delta H FUS equals 333 for something like water. And so now we have all the tools that we need to actually perform this calculation. And so if we just go back and look at our steps, remember step one was we're going to warm the ice up to 0 degrees C. So we're just going to use our Q equals MC delta T. Our next step was to calculate the energy required to melt all of the ice. So now we're going to use our Q equals M times the delta heat of fusion, times our heat of fusion. Third step was heating our liquid water, so that we're back to Q equals MC delta T. Then evaporating our water, changing the water from the liquid to the gas phase. Our Q is going to equal mass times the delta H of vaporization. And then finally, heating the steam, we're back to Q equals MC delta T. Now make note here that the C value, our specific heat, is actually different for solids, liquids, and gases. So far for water, we've been using a specific heat of 4.184 joules per gram degree C. That's the specific heat of liquid water. The specific heat of solid and gaseous water will be different, and those are obviously values that would be supplied to you. That's not anything that you would ever have to memorize. And so to perform this calculation, to actually find out what quantity of heat is necessary for 500 grams of water to be warmed from -50 to 200, we would just calculate each one of these 5 different steps, and then we add them up. That's all we have to do. So let's actually perform this calculation. Let's look at the amount of heat that's going to be required to do this. Let's just shrink down our presentation here a little bit. We're still going to keep those values there because we're going to need those. And let's take a look at each of these phases. And so we have 500 grams of ice going from -50 all the way up to 200. And so so we're sitting first down here at our -50 degrees C. And our first point there, so there's the phase where we're actually just warming the ice. So A to B, we're just warming the ice up. And that's going to be our Q equals MC delta T. And so for portion AB, that's our Q equals MC delta T. We have 500 grams of ice. Now we would have to look up the C for solid water. So we've got solid ice, and we have that right here, 2.108. So 2.108 joules per gram degree C. our delta T, we're going from negative 50 degrees up to the freezing point, the melting point of water, which is 0 degrees C. And so we're increasing our temperature by 50 degrees Celsius. And so we plug those into our calculator. For a value of 52,700 joules. So that's from A to B. Next, going from B to C. So we're starting at point B at right here at 100% solid, moving to point C to 100% liquid. So this is the phase now where we are melting our ice. And so from point BC, our Q is going to equal M, our mass, times our delta heat of fusion. So we have 500 grams. I put in too many sig figs there. There we go. 500 grams times our delta heat of fusion of water of 333 joules per gram. And we get 166,500 joules. And now, once again, we're going to be warming up our water. Going from C to D, we have liquid water. We're going to start heating that up. So CD, our Q, is back to MC delta T. We have 500 grams. We now have liquid water, so we're going to use the appropriate C value for that, 4.184 joules per gram degree C. We're going from 0 degrees, we're going from our melting point of water at 0 up to the boiling point of water at 100 degrees C. So that's our temperature change, is 100 degrees C. 500 times 4.184 times 100 degrees C. 209,200 joules. Now we're vaporizing the water. Along point DE, or along line DE, we're changing the water from 100% liquid to now 100% gas. And so that's going to be our heat of vaporization. So Q is going to equal just our mass times our heat of vaporization. So our 500 grams times our HVAP for water, 2260 joules per gram. Mm. 1.13 times 10, times 10 to the 6 joules. And then finally, our last point, or our last portion along the curve, along line EF. Now we've got steam, and we're going to start to heat it up. Sorry, I'll stick with my color scheme. So we're heating up. So our Q is our MC delta T. Our 500 grams, we look up our C for gaseous water, 1.864 joules per gram degree C. And here we're going from 100, our boiling point of water, up to 200 degrees C. And so our temperature change is 100 degrees C. So we get 500 times 1.864 times 100 for an energy change of 93,200 joules. And so now to find the actual energy change of the entire process, we just add all of these up. So 52,700 plus 166,500, 209,200, 1.13 times 10 to the 6th, plus 93,200. Gives me a total of 1,651,600 joules. As you can see here, it's much easier for us to convert or to think of this over in kilojoules. So we're going to convert this to kilojoules to get 1.65 times 10 to the third kilojoules. That's our final answer. So we just have to add up all the different processes. Now, the important things to keep in mind here are just the big takeaways. Or again, any point that we are heating up along our curve, we're going to use our Q equals MC delta T. We just have to make sure that we're using the appropriate C values. And then along our phase changes, when we're melting, we're going to use Q equals our mass times our delta H of fusion. And in our boiling portion, Q equals mass times our delta H of vaporization. And then we just add them all up. And so that's how we would calculate the heat involved with phase changes. Well, we've mentioned and talked about the first law of thermodynamics already. Just remember that energy cannot be created or destroyed. So energy is conserved throughout a chemical reaction, or a chemical process in general, which means that it's going to be transferred between our system and our surroundings. E is internal energy, or it's just a symbol used for internal energy, depending on what textbook that you might use. We used to use a textbook, the Coates textbook, which used U. I honestly don't remember. Let me double check real quick what our current textbook uses. I'll be right back. And I'm back. Current textbook uses U as well. And so U being the total amount of energy within a system. The kinetic plus the potential energy. We talked about the differences between those. Oftentimes cannot be measured directly, and so we'll look at ways that we can go about measuring these. Our overall energy change is just our final energy minus our initial energy. Shouldn't be anything too groundbreaking there. And we talked about this a little bit earlier, that the overall energy for a system, the overall energy change, is going to be equal to the Q of the system, the heat changes, and the energy in heat flow, plus the work done by the system. And it's this that is sometimes expressed as the first law of thermodynamics. And so ultimately, our overall energy is going to be equal to the heat done, the heat transferred, plus the work that is done. Remember, heat transferred from the surroundings to the system, energy increases. That would be endothermic. Our sign is positive. If work is done on the system by the surroundings, then W would also be positive. Work is done whenever something is moved by against an opposing force. And so that should make sense. I mean, anytime something moves, when I'm moving my Apple Pencil, work is being done. When I do this, I am moving it against gravity. And so work is being done. I'm not going to worry too much about these. We've talked about some of the effect on surroundings and so forth with exothermic and endothermic. We'll take a second just to look at here, sort of relating our heat and work. So what we're doing here is placing a piece of dry ice. Dry ice is solid carbon dioxide. Solid carbon dioxide, dry ice, is unique in that due to its various properties, it will not melt. And so we could take a piece of solid dry ice, I could put it out on my desk here, and it's called dry because it's not going to melt into the liquid phase. It's going to go through a process that we call sublimation, in which it'll change directly from a solid to a gas. skips the liquid phase altogether upon an input of energy. And that energy would come, if we're setting it out, would just come from the ambient temperature in the room, for instance. When that happens, so energy is going to be absorbed by the CO2 when it sublimes. And so we're going to get an energy change. Energy is being absorbed by the CO2. So there's some of the energy. There's our heat energy. But we're also going to do work energy, because as the gas forms, if we have, for instance, a book on top of the bag, gas will form in the system and lift the book up against gravity. And so now work is being done as well. By this system, we have some energy occurring, energy change is occurring as the CO2 absorbs energy. And we also have some work occurring as the book is lifted up. And so this type of work that is associated with a volume change against some sort of resisting pressure is called pressure volume work. And so if we remember that heat, our total amount of energy is our heat plus our work. And so the total amount of energy is the heat transferred plus the work that is done. When we look at the heat of, sorry, I'll come back to that. Enthalpy, when we look at a chemical reaction, I know it seems like I'm jumping around a little bit, we're going to tie it back in here in a second. The heat involved in a chemical reaction is something called enthalpy. We have a symbol H for that. And so if we see H equals whatever, that's the enthalpy, that's the heat of a chemical reaction. Delta H is our change in enthalpy. Now it turns out that at constant pressure, no work is going to be done, which means that the heat flow, our heat flow, our Q, our delta H, means that the heat flow can be considered at a constant pressure. This heat flow can be considered to be the total energy of the system. And so here's where we're going to tie it in. Ultimately, all that's going to mean for us is that when we are looking at energy of our chemical systems, we are assuming, for most everything that we do, we are assuming constant pressure, which means that no work will be done, which means that all of the energy of the systems that we are going to be looking at can be attributed to enthalpy, can be attributed to our heat changes. And so, yes, when we use the term energy, that term encompasses both heat and work. But for our purposes, working with constant pressure, but when we say energy, we're really meaning the heat of the reaction. We are really looking at the enthalpy of these reactions. So we're at a constant pressure. Delta H, the heat, is a state function, which is something that we will be talking about a little bit more in the next lecture. We're not going to worry about it now. But we have to remember that delta H is the H, our change in H is going to be our change in heat from the product to the reactant. And a thermochemical equation, we can start to really get into the heat of some of this matter now, or the meat of it. A thermochemical equation is how we represent the amount of energy flow in a reaction. And so for an example here we have some solid carbon plus gaseous carbon dioxide, plus gaseous oxygen to produce gaseous carbon dioxide. And we see that energy here is also a product of this reaction. And so meaning that energy was released by this reaction as it occurred. In this case, 393.5 kilojoules. So this energy was released, meaning it was an exothermic process. And so sometimes you might see it written like this, where we actually write in energy as a product or a reactant. More commonly, however, you'll see it written like this, where we have our our equation for the process, our balanced chemical equation, and then we list what the delta H was. Now, in this case, we said it was exothermic. So remember, exothermic, our heats are negative because we're looking at this from the perspective of the system, from the perspective of the reaction. This reaction released energy. So it went to a lower energy state. The 393.5 kilojoules was given off. So energy was released, and so we have a negative delta H value. Now, it's also important to note that this heat, this delta H, the enthalpy of a reaction, is an extensive property. It's going to depend on the amount that is given off. We can see here, when we look at our balanced chemical equation, this is 1 mole of carbon, right? The 1 is there, we just don't write it in. So 1 mole of carbon plus 1 mole of O2 gives us 1 mole of CO2. And that releases 393.5 kilojoules. And so if we're starting with 12 moles of carbon, 12 being 1 mole, that's going to release 393.5 kilojoules. However, if we only have 6 moles of carbon, we have half a mole, we're only going to release half the amount of energy. We're just going to release 196.8. If we only have 0.1 moles of carbon, we have a tenth of a mole of carbon, we're going to release a tenth of the amount of energy, 39.4, just a difference there from rounding. And so the enthalpy of a reaction is an extensive property. The amount that you see here, the amount that you see as your delta H value after a reaction, is the amount for this particular stoichiometry, for 1 mole of carbon, 1 mole of oxygen, creating 1 mole of CO2. Those molar amounts release 393.5. Now, what if we reverse this? If we take this reaction and we just flip it, and so instead we're going to say CO2 plus our amount of energy gives us our carbon and our oxygen. So all we've done is just reverse this equation rather than looking at our carbon and our oxygen as reactants. Our carbon dioxide and our energy are the reactants. And so now think about what we're doing. Think about this process. In this process, our energy can be thought of as a reactant. And that means that energy is being input into this system. What did we say in the last lecture about energy being input? Is that endo or exothermic? That's endothermic, right? Energy being input into a system is endothermic, and we represent that with a positive delta H value. And so the energy being input into the reaction is endothermic, so we would represent that with our bottom equation here. Now take a look at what you note between these two different equations. We have our top equation being exothermic. Our bottom equation, which is just the reverse, is now endothermic. Reversing the reaction will reverse your sign of delta H. This is going to be very important for us as we move forward with a couple of different concepts. We're not changing the amount. We still have the same molar amount, so our magnitude of delta H does not change. But reversing the reaction will reverse our sign of delta H. Very, very, very important concept. And so when we're looking at thermochemical equations, they represent the energy change that's associated with, sorry, let me just fix my slide here. That's better. So a thermochemical equation represents the change, so the energy change associated with the chemical process. Our sign of delta H will indicate our direction of energy flow. Is it an endothermic or an exothermic process? And the delta H listed, our enthalpy change for a reaction, is extensive. The actual amount of energy that will be transferred will depend on how much of our limiting reactant that we have. And the equation that we see, our thermochemical equation, and the delta H represents is representative, of the number of moles in our balanced chemical equation. And so, for instance, we see a different equation here. So here's our formation of ammonia. We have our balanced chemical equation. We have a delta H value for that. We can see that it's exothermic. It's going to release energy. But this 92.22 would depend on having 1 mole of N2, 3 moles of H2, and 2 moles of NH3. One of the things that you might be seeing about chemistry by now is that oftentimes we'll introduce a concept or introduce a rule and say, this is the way it is, and then we make exceptions to that later on. Now we're going to make an exception to that, to something. Remember when I said back when we were looking at balancing chemical equations, I said that equations must always be balanced with whole numbers? Well, in thermochemical equations, we can actually use fractionals, numbers for our coefficients. And if we do that, if we change our molar amounts in the equation, we must then adjust the enthalpy accordingly. So let's take a look at what I mean there. So here's our same equation. And so this equation is written, again, for 1 mole of N2, 3 moles of H2, giving us 2 moles of NH3. For whatever reason, and we're going to see some reasons we might want to do this probably in the next lecture when we discuss Hess's law, but there might be times when we might want to know how much energy is released for just 1 mole. They're creating the formation of 1 mole of NH3. And so we would have to adjust our equation accordingly. And so if our equation is N2. So our equation is N2 plus 3H2 forming our 2NH3. Sorry, I didn't leave myself enough room, so I'm just going to go back a little bit. Just need to adjust my screen sizes here. Technology is messing with me a little bit today. Here we go. Okay. N2 plus 3H2 giving us our 2NH3, and we said that delta H for that is equal to negative 92.22 kilojoules. But now we're saying that for whatever reason, we want to know the energy that is released if we only form 1 mole of NH3. So to form 1 mole of NH3, that means we have to divide everything through by 2. Because in order to form 1 mole of NH3, I'm only going to need to start with half a mole of N2 and 3/2 of a mole of H2. And that's, so I'm looking at only forming 1 mole of NH3 instead of 2 moles. That's going to cut my delta H in half. And so this would be my thermochemical equation for the formation of 1 mole of NH3. I might want to know for some reason the amount of energy to form or to decompose 4 moles of NH3. So decomposition, now I'm splitting up. Now I'm looking to reverse my reaction. And so my initial reaction in reverse, 2NH3 to form an N2 and 3 H2s. And remember what I said when I reverse a reaction, we have to reverse our sign of our enthalpy. But we want to know, we don't want to know about the decomposition of 2 moles, which is what our equation is now. We want to know the decomposition of 4 moles. And so we're going to multiply this whole thing through by 2. Which means that we now have to double our enthalpy. Then as a last example, if we want to know, for instance, just the thermochemical equation for 1 mole of H2. So if we're only adding in 1 H2, that means we have to divide everything through by 3. And so we would have 1/3 N2 plus 1 H2 would then give us 2/3 of NH3. And our delta H, unfortunately, I can't do 92.22 divided by 3 in my head. negative 30.74 kilojoules. And so moral of the story here is that when looking at a thermochemical equation, it is okay to have fractional coefficients. And we're going to see why we might want this in our next lecture. So we're just introducing it now, so it's not going to come as a surprise for you at that point. Now, when it comes to actually finding thermochemical data, when it comes to being able to find the delta H value, there are several ways that we can go about doing so. We're going to talk today about measuring it directly by performing a reaction and measuring the amount of energy that it gives off using a method called calorimetry. We're also going to talk next time about finding the thermochemical data for an equation using other equations for which we do have data already. And that will be using something we call Hess's law. And then lastly, next time we'll also talk about using something we call heats of formation for the products and the reactants. So let's take a look at calorimetry today. And so we're measuring our heat flow. Calorimeters in general can be thought of as closed systems insulated from an outside environment. For our purposes, we can think of it as if we were doing a calorimetry experiment in our 114 lab, we would probably do so with 2 coffee cups nestled together with water inside. And so any reaction that occurs inside this calorimeter, or if a reaction occurs inside the calorimeter, any heat generated by the reaction must be absorbed by the contents of the calorimeter. So in other words, let's take a look at that. So here we have just a couple of styrofoam cups nested together, a bunch of water inside. And so the reaction, any reaction that occurs in the water here, if that reaction is exothermic, if that reaction releases energy, that energy is going to be absorbed by the water. And so let's think about that. So here we have, and we've already sort of looked at this and thought about it, but we're going to start to quantify some of this a little bit. So here's our calorimeter with our water in there. So here's our water in our calorimeter. And with a thermometer down in here. So we can measure any temperature changes. But then let's say we run a reaction. So here we have a reaction happening in our water. That reaction, say it's exothermic, it's going to release energy. Now we don't know how much energy is released directly, but what we can do is we can measure the effect that that energy release has on the contents of the calorimeter, the effect that that energy release has on the water. Now we do have a way to measure the energy gained by the water, right? We've talked about that pretty extensively at this point. Our energy that's better. Our energy gained by the water, we can just calculate using our old friend Q equals MC delta T. Because we would be able to know pretty easily how much water is in there. We can know the mass of our water. We know the specific heat of water. And then we can use our thermometer to measure the temperature change. We also know from the law of conservation of energy that the heat gained by the water is equal and opposite to the heat lost by the reaction. And so if we can measure this amount of energy that is gained by the water, that will be equal and opposite to the amount of energy lost by the reaction. And so if we have a certain process that can happen in water easily enough, we can run that reaction in water, measure the temperature change associated with the water, and there we go. We can calculate the heat that was then given off by the reaction. So let's take a look at an example. And so here we have 6.1 grams of solid sodium hydroxide. We're going to dissolve that in 100 grams of water, and we have a temperature change from 21.6 to 37.8, And we want to calculate the delta H, we want to calculate our enthalpy in kilojoules per mole of NaOH for this process. So again, let's just sort of remember what we have. We'll keep this little diagram up here. We've got our water in here, and we've got our process happening here. And what we're doing is we're taking our process for this example. It's just NaOH solid going to NaOH aqueous. And we want to calculate our delta H. The temperature is rising. The temperature of the water is rising, so that tells us that it's an exothermic process. Energy is going from our process, from our reaction, out into the water, raising the temperature. And so we know then, just like we've been talking about, that the Q gained by the water is equal and opposite to the energy lost by the reaction. And so let's calculate our heat gain by the water. Q equals MC delta T. We know how much water we have. We're told that we have 100.0 grams of water. Our C of water, 4.184 joules per gram degree C. Our temperature change of the water goes from 37.8, or sorry, ends at 37.8 from 27.6. And so our energy change of the water gained 6778.08 joules. We know we'll eventually want this in kilojoules. We might as well convert this now. 6.77808 joules. You'll note that I'm keeping more significant figures than I'm going to need because my calculation's not done yet. We're not asked to just find kilojoules. We're asked to find kilojoules per mole of NaOH. The NaOH that we added into this, we know we added in an amount of 6.10 grams. That 6.10 grams resulted in an energy change of 6.77808 kilojoules. So now we just want to convert that 6.10 grams over to moles and then divide our energy change, divide our kilojoules by that number of moles. So we're just going to take our 6.10 grams of NaOH, use our molar mass of NaOH to find that we have 0.1525 moles of NaOH. So finally, we're going to take our 6.77808 kilojoules divided by 0.1525 moles for a final of 44.5 kilojoules per mole. Now we have to remember here, so we remember what we've calculated at this point is our heat gained by the water. This is one of the reasons we have to be so careful with our signs and be careful that we are putting our temperatures in correctly, our final temperature minus our initial temperature, because we've ended now with a positive number. That was our heat gained by the water. So it would make sense that that's positive. That equals the negative heat lost by the reaction. And so the actual heat of the reaction is negative 44.5 kilojoules per mole. That is our final answer. And so we always have to remember that direction of energy flow, that what we're calculating first is the energy in relation to the surroundings, which will be equal and opposite to the energy from the system. Okay, sorry. So another example here. And so in this example, we have 4.25 grams of ammonium nitrate dissolving in 60 grams of water. And we can see here that the temperature of the water actually drops. The temperature gets colder. And so we want to calculate the enthalpy change, calculate delta H for this process, and write the resulting thermochemical equation. So pause the video now and do this. Try to do this this calculation. See if you can come up with the right thermochemical equation. I'm going to show the answer in just a minute. So take a second to run this calculation. Pause the video, run the calculation, see what you get. Hopefully you got this. And so here's our general equation: ammonium nitrate as a solid, ammonium nitrate aqueous. And we can see that our delta H is positive 25.8 kilojoules. It's an endothermic process. And that would make sense because the temperature of our water went down, our water got colder, because energy went from the water, from the surroundings, into the reaction. And so the water got colder because the energy went into the dissolving process. Lastly, let's leave today by looking at what we call bomb calorimetry. The coffee cup calorimeters that we've described are fine for rough measurements, and they'd be fine for if we were running this in our educational lab. But there are times that maybe the reaction is too dangerous to carry out in a coffee cup, or we want much more accurate results. Because the reality is that when we look at this coffee cup calorimeter setup, when we look at let's go back for a second. When we look at a setup like this, let's think about a baseline assumption that we make. We're talking about the energy of our system being then absorbed by or released into the water. The calorimeter, the coffee cups, are going to play a role in that as well. If we have an exothermic system where the reaction is giving off energy, then yes, most of that energy is going to go into the water, but some of that energy is going to be absorbed by the calorimeter as well. For the processes that we've talked about so far, or if we ran this in an educational lab, it's not going to absorb enough to really interfere with our calculations. But if you need real precise thermochemical data, real precise calorimetry data, then we would use what we call a bomb calorimeter, which is a much more extensive setup. You see it looks very similar to this here, in which we really encase all of the water. And then we have our water in here. And then we have what we call the bomb, where the reaction is going to take place. Some of the energy will be released into the bomb, and some of it will then be released out to the water. And so when we're looking at using bomb calorimetry, when we're looking at really getting these very precise results, we now start to take into account the energy that is absorbed by the bomb as well, that is absorbed by our calorimeter. And so the ultimate energy of the reaction is going to be equal to the energy of the bomb plus the energy of the water. To find the energy absorbed by the bomb, we just take the specific heat of the bomb times our temperature change. And so that's a simple addition to this, is now instead of just looking at the temperature change of our water, we are also going to look at the temperature change of our, instead of just looking at the heat absorbed by the water, we're also going to look at the amount of heat absorbed by the bomb. So let's look at an example. And so here we have 3.30 grams of glucose, C6H12O6, placed in a bomb calorimeter. And the temperature of the water changes from 22.4 to 34.1 degrees C. We know the calorimeter contained a certain amount of water, and the additional heat additional information we're given here is we now have the heat capacity of the bomb itself. So we have the heat capacity of our calorimeter. And we want to know the delta H, the enthalpy change, for the combustion of 1 mole of glucose. And so what we have to recognize here and work with now here is that the heat of our reaction, the Q of our reaction, is going to be equal to negative to the opposite of the heat gained by the water plus the heat gained by our bomb. Remember that we said that we calculate the heat gain of the bomb just by multiplying our mass, times our temperature. Sorry, I'm thinking about too many things at once. Remember, our Q of the bomb is our C of the bomb, our specific heat of the bomb, times our delta T. This is an easy enough calculation to do. And so our Q of the reaction is going to then equal our Q of the water, MC delta T. We have 850 grams of water. C of water. Our delta T of the water, 11.7 degrees C. We're going to add in the Q of the bomb. We know C of the bomb, we were given that in the problem, 847 joules per degree C, times our temperature change of 11.7 degrees C. So we look at each of those, we do out the math of all of this, and we get a total amount, our Q of the reaction, of 51,519.78 joules. Probably want to convert this over to kilojoules. That's easy enough to do. 51.51978 kilojoules. And so that's how much energy was given off by 3.3 grams. We want to know the delta H in grams per mole. And so we're going to take that 3.3 grams, convert that over to moles. We do that. I won't show you that calculation because we've seen that a million times at this point. But we get 0.0183 moles. And so we're going to take our 51.51978 kilojoules divided by 0.0183 moles for a total of positive 2,815 kilojoules per mole. But remember that this, what we just calculated, was our Q of the water and the bomb. And so the sign is going to be opposite that for the Q of our reaction. And so the actual Q of our reaction, and now adjusting for significant figures, the Q of our reaction is going to be negative 2820 kilojoules per mole. And that is a calorimeter, bomb calorimeter problem, negative 2820 kilojoules per mole. And so that is the basics of energy for today. And so calorimetry, like I said, is one of the methods that we have of finding the thermochemical data for a process. We could write out this combustion reaction if we wanted to now. In fact, let's go ahead and just do that. We'll take one more second to write this out. And so we have our combustion of glucose, C6H12O6 plus O2 gives us our carbon dioxide and water. And if we balance this, we have this, and we now have the extra bit of information. We know our delta H value is negative 2820 kilojoules per 1 mole of glucose. And so this would be our full thermochemical equation. If I actually did it correctly, so it was all on one line, I'm just going to be anal and rewrite it. So there's our thermochemical equation for the combustion of glucose, and measured by calorimetry. And so next time we will talk about some other methods to find this thermochemical data. And so until then, work on some of the problems and I hope you have a good day.